Thank you very much. So I realize that people are going to have a major sugar crisis and chocolate crisis, so I'm going to try to stay animated and tell you about COVID-19 and Disease X and how what we've learned from COVID-19 can help prepare us for what probably lies ahead. So the rest of the world is probably quite ready to move on from COVID-19 and stop thinking about pandemics, but everybody in this room, people that work on infectious diseases and people that work on vaccines, are very aware that there are additional threats out there. And this is a slide from several years ago from a paper in Nature that went through dividing up emerging infectious disease events over the decades. And they started from 1940 and went to 2000. And the top left is the pathogen. So breaking it down, the black are bacteria, the white are viruses, and the that peachy color are protozoa. So you can see that viruses and bacteria account for the vast majority. To the right-hand side, B, are transmission type. And here they're divided up into zoonotic and non-zoonotic. So non-zoonotic are the black, zoonotic of various versions are above the black bar. There's drug resistance and the transmission mode, which is vector-borne versus not. So for years now, we've known that zoonotic infectious diseases pose a very significant threat. There are a number of factors that account for this, both on the virus side and the host and the environment. And in this concept of One Health, we really need to start integrating lessons from all three because we really cannot prepare for a future epidemic or pandemic until we take into account what's happening in the environment around us. So the microbial agents can certainly change. We can have polymicrobial diseases. We can have genetic adaptation of pathogens. But within the human host, you've heard about human susceptibility from underlying health conditions, human demography changes, there's international trade and travel, there are occupational exposures, and there's certainly exposure, inappropriate use of antibiotics. And then on the environment side, certainly climate change is something that we need to think about a lot. Changing ecosystems and technology and industry, there's a lot of inequities in health across the world. And we must pay attention to what's happening with animal populations. In today's world, we need to be more worried about what war and famine will do. And there is, across the board, there needs to be a political will to work on these problems. So when we think about the determinants of disease emergence and reemergence, they're overlapping, it's part of an overlapping Venn diagram where we've got the host, the agent, and the environment, as I've said in the last slide. And this is a review by David Morens and Tony Fauci that was published in Cell just after the COVID pandemic began. They've looked at molecular mechanisms that account for host switching. So why do zoonotic agents emerge into human populations? And there are a number of different mechanisms. There can be a progressive change in the pathogen during adaptation, or there can be a chance transmission where a pathogen has acquired a number of advantageous mutations. So with that background, this is a summary in 2020 from that same review, looking at emerging pandemic diseases from 81 to 2020, and they're color-coded into newly emerging in red, re-emerging in blue, and deliberately emerging in black. And so, you can see just looking at it that it is a very busy world. And as I said, no one really wants to think about this coming straight out of COVID, but we do need to consider the landscape. So I was at this meeting in 2020, and that was when I first heard about the possibility of transmission of COVID-19 from people that had been asymptomatic. And I remember thinking to myself then that this virus was behaving more like an influenza virus and not like MERS and SARS. And I thought, boy, are we in trouble now? So this is a slide that comes from this Center for Health Security at the University of Pittsburgh, and it just outlines the traits of potential pandemic pathogens. The ones that we need to be most concerned about are pathogens to which there's no pre-existing immunity in the population, those that are airborne spread, those that are silently spread, and those that are harmful. So this is just, they've cherry-picked what they're and I thought the pictogram was very easy to communicate with. So what are the lessons that we've learned during the COVID-19 pandemic? It was a novel coronavirus. Very quickly, it was established what the receptor was. The receptor is ACE2, but that's shared. That receptor is also used by SARS coronavirus 1, or what used to be just called SARS-CoV, and NL63, which is a human coronavirus that causes respiratory illness. The big difference between SARS-1 and SARS-2, but probably along the lines with NL63, is that the virus is efficiently transmitted from person to person. Asymptomatic and mildly symptomatic people can spread the virus, but super spreading events certainly did occur, and I think we need to understand them better. Super spreading events tend to be something that we diagnose in retrospect, and it would be really nice to know what those determinants are, whether they're factors in the host or factors in the environment. What is it that makes super spreading events happen? There's been a lot of discussion about transmission, and there was a huge amount of resistance to the idea of airborne transmission for SARS-CoV-2. And here we are, we've accepted it, but now we're questioning whether that's true for flu. And I don't understand why we're asking that question still. So we do need to relook at what we knew and what we thought we knew about other respiratory viruses, having learned what we have from COVID-19. So there are many successes and challenges with SARS-CoV-2, and I've just outlined a few. Certainly molecular diagnostics, next-gen sequencing, and data sharing was incredible. In the flu world, we had not seen so many labs around the world being able to do molecular methods for diagnostics or next-gen sequencing, and it is really a changed world. And generally, people really did share their data freely. There's been a huge improvement in vaccine development, both the rapidity and the number of platforms that are available. We focus a lot on mRNA. It didn't come out of it wasn't just born yesterday. There was some development work going on for several years. But I think one of the things that we did learn during the COVID-19 pandemic, and this is thanks to the manufacturers and regulators working together, was that very rapid clinical trials were conducted, and there was a new regulatory approach to approval of vaccines, so that you didn't have to do the step-by-step, finish phase 1, then go to phase 2, and then go to phase 3. It was much more accelerated. And we probably will see that going forward in the next public health crisis. We've certainly seen adverse events. We've seen myocarditis, pericarditis, TTP, and that has certainly caused problems with vaccine uptake. The emergence of variants was a big surprise. I think we were all hoping that, like measles, we would have one vaccine that would serve us well for 50 years. Not so. We also thought it wasn't just a pipe dream. We thought this might be the case because coronaviruses actually have a proofreading capability in their genome. So we really had hope that we would get by with one vaccine. And that has certainly not been the case, and I'll talk a little bit about that. To me, I think one of the saddest parts of the last few years has been the inequities in health. Inequities in access to care, inequities in accessibility to the vaccines that we take for granted here. And then there's the poor uptake even when you do have the vaccines available. The other area that I think has also changed a lot in the last few years has been the monoclonal antibody area. So in flu, we've really not considered antibodies to be a major part of our prevention and treatment strategy, in part because we know the hemagglutinin changes, and it changes rapidly. So why would you make a product that the virus could then escape from? But what we've learned in the last few years is that there have been tremendous advances in antibody engineering. And so now, if you make an antibody and you deliver it for passive immunity, that passive immunity can last 6 months, which is not that much less than what mRNA gives you, depending on what your outcome measure is. So I used to just kind of think, oh, well, passive antibody or passive immunization is useful in very, very specific niches, but I've changed my mind about it. I think it's very impressive what has been done with the antibodies. Of course, we do have to deal with immune escape variants, so you have to identify epitopes that are not under pressure to change. So I've been working quite closely with the WHO on SARS-CoV-2, and they were, not arguably, quite clearly, a bit slow to get organized. But they have gotten themselves organized, and they've organized themselves around a couple of different advisory groups. So they have an area where there's a group, they focus on monitoring and surveillance, and they have a technical advisory group on virus evolution that specifically looks at what variants are circulating, and when variants are identified, how are they going to affect the use of diagnostics, the use of antibodies or treatment, and the use of vaccines. Then there's the vaccine part, which again now looks at what the effect of those changes are on the vaccine and should the vaccine be updated. And that is done by two groups. There's a blueprint for epidemics, and there's TAG-COVAC that I'll talk to you about more. The actual recommendations come from SAGE, so the policy recommendations come from SAGE, and you heard Annalise Wilder-Smith, she's one of the people that works closely with SAGE. So the WHO put together this technical advisory group on COVID-19 vaccine composition that I've chaired since it began, and I'm hoping to hand that over soon. It's a group that started off with about 18 people. We're 16 now. And I think they're taking some new members soon. And our job is to look at new variants that have emerged and decide when and whether the vaccine needs to be updated. So this has been quite a challenging committee because the only vaccine that is updated regularly is influenza vaccine. So you would think that we would take lessons from influenza, but we had a significant pushback even on the committee saying, why would we talk to people in flu? So we've now come together and we've got this working. So we've written this up in as a perspective piece or a commentary in Nature Medicine, explaining what the TAG-VE does, how we're thinking about it. And so essentially the TAG-VE, which is the virus evolution group, when they identify a variant of concern, and I think the WHO is changing that nomenclature, so it's just going to be a variant of interest or a variant of concern, that triggers us to think about whether that's going to have an effect on our vaccine composition. So at this point, we rely on data from the academic community and from vaccine manufacturers because unlike the WHO flu system, we don't actually have the equivalent of GISRIS. So we're very reliant on governments and independent investigators, as well as the vaccine manufacturers, to share their data. I think this will have to change going forward because many governments are pulling back on their investments in COVID-19. But we rely on these data, and then we sit down and we assess the antigenic characteristics of the new variant. We look at what evidence we have that the previous vaccine would provide protection or provide cross-protective immunity against the new variant, and then we publish that. So to give you an example, when we first started, we weren't sure when the Delta variant emerged, and then Omicron emerged after that, that was the first time we were thinking about making a vaccine composition recommendation. And we first started meeting about Delta, and then 2 months into it, there was Omicron. So we had to do a quick switch to start thinking about Omicron, but we didn't actually know whether going forward in the future, the virus would flip back and a new variant would come off the Delta lineage, or whether we would keep following in this path along where Omicron is. And what we do know now is that we are following in a stepwise evolution. We're not flipping back to the earlier variants. So that is something that is changing. So we're a little more comfortable, which is, the first recommendation we made, we recommended a bivalent vaccine because we weren't sure whether it would flip back. But now we've gone to a monovalent recommendation in order to sort of keep up with this evolution. The other thing that's really changed is hybrid immunity. So we now know that if you get vaccine alone, you get a certain level of protection, but with hybrid immunity, you get much greater protection. So this complicates matters because, in fact, today, 90+% of the world's population has some immunity against COVID-19. So the good news is that people have a lot of background immunity to COVID-19. The bad news is that it's very hard to do studies to understand the impact of mutations on protection. So this is across the world, studies done at different time points. The overall rate of seroprevalence in the world is very high. So we put all this together. We're meeting twice a year. We don't want to set in stone what that 2 times a year is, because although there's a periodicity to the emergence of variants, it's not true seasonality. And so the Northern Hemisphere, Europe and the US has pretty much decided that they want to vaccinate before the winter begins. So it's an easy one for them because they know when they need vaccine. But for the rest of the world, we're really less sure about when that should be. So we are continuing to have a second meeting, in addition to monitoring data the rest of the year. We are having a second meeting roughly 6 months apart, and we meet with vaccine manufacturers for discussions. Whoa. Okay, so what is disease X? So I did notice that very few people put their hands up to say they knew what disease X was. It's a name given to an unknown pathogen that could emerge in the future and cause a serious epidemic or pandemic. This name actually came up before COVID-19. It was already floating around. Does it exist? It is hypothetical, but the concept describes a real and growing threat to human health. When will it happen? So of course this is the big unknown, but interestingly at CEPI's website they say the chance of a pandemic with an impact like COVID-19 is 1 in 50 in any year. And the lifetime probability of experiencing a pandemic like COVID-19 is about 38%. And environmental changes will increase that risk. So will disease X cause the next pandemic? We don't know. It could be this. It could be reemergence of a previous pathogen that we know, or it could be a new one. Where is it likely to come from? So what several groups have done is they've identified 25 virus families that they believe are likely to give rise to disease X. How can we prepare? We need to learn as much as possible about those 25 virus families and at least pick a prototype from each and learn about the pathogen, learn about the immunity to the pathogen, and how to make a vaccine. And CEPI has declared a 100-day mission, so it took them 326 days to make a vaccine for COVID-19, and they have made a very aggressive bid to bring it down to 100 days. So the UK put together this list back in 2019, and they've overlaid what the WHO picked, what CEPI picked, and what NIH picked, and what the UK Vaccines Network picked as their key targets. The NIH more recently published a report where they looked at the pandemic potential going from low to high, and on the vertical axis, it's whether you have what the existing resources and countermeasures are. So you've got this box that has high pandemic potential, but also a lot of resources on it, and that's flu and COVID and coronaviruses. And then there are others that are low, so low pandemic risk and low resources. So they're focusing more on these two groups, where the pandemic potential is high, but the amount of investment is low. So the NIH's prototype pathogen approach is to identify these viral groups, select a pathogen from amongst each one, do the basic preclinical and translational research, and advance into clinical trials as rapidly as possible. And they've identified research gaps. They had a workshop, and this is the product of that workshop. They've identified research gaps where what basic research is needed, how much disease modeling and animal model development is needed, and then avenues to manufacture and develop and deliver vaccines. So one strategy that was described in 2022 was that we need to take steps to reduce the risk of spillover and consequent introduction and spread into humans. We need to improve disease surveillance in animals and in humans to rapidly detect and sequence the infectious agent. We need to strengthen research programs to shorten that time lag. We need rapid implementation of pharmaceutical and non-pharmaceutical measures to contain large-scale epidemics, and international protocols to ensure fair distribution and global coverage of drugs and vaccines. So GISAID is the sequence database that was developed for influenza but is now used for many different pathogens, and they've sort of outlined how you could actually start when you have a new pathogen, figure out if it belongs to a well-characterized family or not, and learn from the other family members that you know something about to build a plan going forward. So this is close to the end. The lessons from COVID-19 are that we need to explore different vaccine platforms. We clearly need some more research and development, even on the mRNA. We need broadly accessible adjuvants. We need distributed manufacture across the world and sustainable production. We need regulatory engagement, flexibility, cross-reliance, and collaboration, rapid sharing of data on sequences, animal models, and immune responses. We need international standards and clinical trials which are coordinated multi-center studies. The WHO's R&D blueprint held a series of webinars last month, and this is the summary from that. So I will close by thanking all of you for your attention. I have been at the WHO Collaborating Center since the end of 16, and I'm going to pull up stakes and move to the cold, wintry Canada. It's only a partial move. My research lab that's pictured on this slide at the Doherty Institute, I will stay associated with that lab, but I'll be stepping down in a few months from the WHO Collaborating Center. So on a personal note, thank you very much. I've enjoyed being part of these meetings, and it's -17 in Quebec right now, so do think about me. I don't know that I want to be here on a 38-degree day, but probably better than a -17. So thank you very much.
Kanta, thank you. It was like being in the war room, to see the preparation that is being done behind the scenes and highlighting the risks. We've got time for a couple of quick questions.
Thanks, Kanta. I'm very sorry to see you going. There's one coming though. Yeah. I just wondered, with the business, as you said, hybrid immunity seems to be the best. And I don't know there's an answer to this, but does it matter which order you get them in? Is it better if you have is it better if you have an infection prior to vaccination, which has been discussed around flu, or does it?
So that's a really good question, because one of the issues is if your first experience with a pathogen may set the stage for how you respond to subsequent exposures, and that's referred to as immunologic imprinting. So what would be very valuable are studies in cohorts of people, and Australia probably has such cohorts, where young people, young adults, may have had their first experience ever with Omicron. So they may not have been vaccinated before Omicron came through, and it would be really interesting to contrast their immunologic experience with those whose first experience was with the ancestral strain.
Thanks, Kanta, and we will be sad to see you go. In the early days of being on TAG-COVID, you were saying that you were not keen on chasing variants. Now that you've seen what's happened, have you identified like a trigger point at which you might say, yes, actually it's time to be looking to develop a new vaccine?
Yeah, so I'd like to clarify. What we've said is we wanted to get away from this idea that we were trying to predict where the virus was going to go, and that we would, and if by the time you manufacture a vaccine, the virus is evolving. And so we wanted to get away from this idea that we're already wrong by the time the vaccine's made. And so what we wanted to emphasize is that our goal is actually to broaden immunity. So by choosing the next immunogen that would broaden immunity rather than chasing the individual variant. So there's no doubt that our activities are triggered by the emergence of variants that show evidence of immune escape. So we now know, just like we do for flu, that there are certain hotspots. We know some residues that if they change, we're like, okay, we know we're worried about this one. But not every one of those variants ends up being fit or being able to spread widely. So we do have some trigger points, but we're not trying to catch up with or choose a specific strain.
Ian.
So, Kanta, disease X, 25 is a heck of a big number to be working on at any one time. I'm glad to see NIH have 2 lead candidates, orthomyxo and coronaviruses.
No, they think they've already spent enough money on those.
Well, they haven't.
So it's the others.
No, they haven't, and they should spend more. And the other one, which Eddie Holmes puts in, is paramyxos. So should we be focusing on truly pandemic potential viruses, or do we really waste, well not waste, do we really expend our efforts on 25 at a time?
Yeah, no, I really think that no one has deep enough pockets to do 25 at a time. So I think this idea that you actually make a grid and say, what is there reasonable investment in now, and what are some virus families that we don't know enough about? And those should become the high priority. So WHO is going through an interesting exercise right now, and some of you in the room may have been called in for these consultations, but they've gone virus family by family, and they're polling people to say, which of these do you think you would put on the list? So it's planning by committee, which I'm not a big fan of, but I do think that we have to narrow that list.
Kanta, is something like long COVID just a hangover of, or can it be a feature of disease X?
That's interesting. I don't think that there's been a lot of talk about chronic disease, but if that turns out to be what they find with other virus families as well, because it is debilitating and it is a huge economic burden. So again, just like we didn't expect the virus to spit off variants, we didn't expect this long-term illness either. So it's something we have to learn about. Yes.
Last question.
I'll shout. Was there a lot of discussion about diagnostics in the WHO's consideration? Because vaccines are very groovy and expensive. We spent a lot of time early on in the COVID pandemic diagnosing public health follow-up before vaccines really became available. And crucial to that was diagnostics and a whole lot of other things that aren't quite so groovy. Was there much discussion about that or not?
So I think there is, but not in the groups that I'm involved in, because certainly TAG-VE, the virus evolution group, they look at kind of these S gene failures and things like that, the impact of variation on the existing diagnostics. But I think the R&D blueprint also pulls together a number of people on diagnostic development as well.